All right, so this is going to be a brief video for differential equations. I was happy to go over this very briefly with you guys in class, so that way you guys could see a little bit of what differential equations are, especially since they have such a large bearing on the exponential function. So what we have here are some examples of differential equations down at the bottom of the screen. And I'm just going to speak a little bit about what differential equations are at the beginning of this, just so that way I can have you guys all on the same page in case you guys missed what I was saying in class. But it's basically a relation between the derivative of a function and any potential variables, constants, or maybe even the function itself, which would describe what the function is, rather than having the function explicitly given to you. And so some of these equations that you see down below, such as dy over dx equals ky, this is a description of what the function is without explicitly stating what function y is. It's related to the derivative by this equation, but there's no explicit function that it's stated for what it is. And we'll see later that this particular differential equation is useful for the exponential function, or can be related to the exponential function in a way, and a way that we've actually seen prior to this in this course. But let's take a look at the other examples really quickly as well. So if we have y double prime minus x times y prime plus x squared equals 5, this is a relation between the second derivative, the first derivative, and the variable x and a constant. All of that is fine for a differential equation. It's a little bit more of a complicated differential equation than we're going to be able to figure out how to solve in this class. But this is a potential differential equation that you might see if you were going to go into if you were going to take a class on differential equations. And this would be one that you would be able to solve with maybe a little bit of effort, but it would be one of the first ones that you kind of run into. So let's also take a look at dy dx equals 2xy. This is another one where you have an x in there, but you still have the y function not explicitly stated. And so it's still related to what the derivative is for the function, and that gives you enough to be able to find a cases, which would be solutions for this function. But it doesn't have the function explicitly stated. And so this is another one of those cases where you'd be able to figure out what it is if you were going through the methods that you would learn in the class for differential equations. But this is not an explicit definition of what y would be, just as it is. All right, let's go ahead and take a look here at how that relation that I mentioned earlier can actually be used with something we've learned previously. So when we're talking about exponential growth, we're actually talking about something that's a solution to a differential equation. And so when you're talking about exponential growth has the property that its derivative is related to the value of the function by some constant. And so we have this situation where the derivative is equal to the original function times some constant k, or some constant, in this case, r. And that r constant can actually be written into the exponential function in such a way that you'd end up with the exponential function for the compound continuous interest formula. And here in this one, I'm noticing I've got this written in terms of dx. It actually needs to be in terms of t if we're doing it where we have t as our time for our exponential. So be careful about that. Sometimes when you're jumping through, and the way that I've been doing it, I've basically been taking what's in the book and trying to convert it into what we've been talking about. And in this case, I just missed that, where it's written as x in the book, but in terms of how we have been thinking of it. We've been thinking of it in time. So just be careful about that if you're trying to write it down. In regards to this particular situation where we have Q equal to Q naught times e to the RT, this is our compound continuous interest formula, just with slightly different wording. And so we have our Q being our amortization, or our final value of the function. We have our Q naught being our what would be our principal value. And then we have our e to the RT, so our rate and our time at the exponent for the exponential. And if we're looking at Q and we wanted to take the derivative of Q, our dq dt would be r Q naught e to the RT. And so that result there would give us the relation that r times our original function is equal to that derivative there. And that's just a property of the exponential function, exponential growth. And this is how you can kind of see where a situation that you have a derivative equal to some constant times your value of the function would relate to a differential equation situation, because you have that relation of a differential equation. And so if you're interested in trying to solve things that might be a little bit more complicated, relations between their derivatives and functions and things like that, then going into differential equations is a good idea, or taking a differential equations class is a good idea. So there are a lot of things that end up having differential equations in them. Some of them might be a little bit more complicated in their writings and such, or there might be more complicated forms of the exponential function written into it. But there's such things as depreciation of equipment, the sale of new products, company growth, long-term population growth. The book even recommends a particular form of the exponential function called logistic growth for epidemics, which is timely at the moment. And so if you're interested in trying to model something such as COVID or other disease spreads, you could look at logistic growth, which is a different way of writing the exponential function, so that you actually have like a cap, such as a population maximum that exposure could happen at. There's also price demand curves, atmospheric pressure, radioactive decay. All of that relates to exponential decay. There's short-term population growth, growth at money and compound continuous interest, and price supply curves. That's unlimited growth with an exponential curve. So if you're interested in any of those things, you can kind of take a look at the specific cases that have to do with each of those individual types of models. And if you're more interested in one of those specific ones, you can come and talk to me and I can point you in the right direction to deal with it or to investigate it. So, all right, that's about it for this section, and I'll see you on the next one.